we'll break in gently. Good afternoon, everybody. We had a session yesterday which was about electrical interference assessments for alternative energy supplies. And today we're going to talk about high voltage DC, which is something a lot more complicated, really, and it's an increasing problem for us. Only I could get this to move. I want this. Oh, there we go. Right. So just to let you know that this is made on behalf of the Onshore panel of the Pipeline Industries Guild, and we have done quite a few of these now. My joint author on this is Professor Charalambos from the University of Cyprus, who's done a lot of work on these kind of things. We do quite a lot of papers together, and we work on several ISO committees together. The previous webinars in this series are listed here. You might, if you feel that some of the background is missing from the HVDC on the basics, if you go back to these webinars, you might feel a bit more encouraged. Now, this is complicated, and I've tried my best to simplify it, but I've created a little scale of nerdiness and complexity to encourage you. And the bottom of the list is statistics. Train spotting, that's pretty nerdy, but not as nerdy as we're going to go. Stamp collecting, same sort of thing. Apologies to any train spotting stamp collectors here today. Calculus is a bit nerdy. Cathodic protection is a bit more nerdy. Amateur radio is even worse. Rocket science, brain surgery, space physics, DC interference, AC interference, and the top of the tree for nerdiness and complexity is high voltage DC. So don't get too disappointed or cheesed off if it doesn't all fall into place straight away, because it is incredibly complex compared with the other systems that we've looked at. We're just going to have a gentle run through today with the obviously a bit of an introduction, something about the configuration of the systems, because they come in many different shapes and sizes, all with different electrical problems. And I'm going to summarize a little bit DC interference and corrosion and electromagnetic interference, and then, like all good stories, we'll have an ending. So the first question you might want to ask is, why do we use HVDC? We've got plenty of overhead power lines, although not enough to meet this mad rush demand for alternative energy and electric cars. But we've got a good existing network of overhead power lines, the ones that you see up in the sky with all these big insulators on. But electricity comes in two different flavors. It comes in DC and AC, and DC is easy to understand because it's just a direct current system that doesn't change its polarity, and it just follows the circuit it's given and behaves itself. But when it comes to AC, you actually have things like reactance. It doesn't just see resistance, it sees reactance. And it has changing magnetic and electric fields with it. There's a little thing called skin effect, which isn't acne in this case, but it's a feature related to the frequency of the AC, and it doesn't utilize the entire cable size, whereas DC uses the entire cable size. So when you do a cable sizing for AC, you have to make an allowance for the fact it won't use all the cable. So you can see you've got savings in cable sizes. AC systems can become unstable over long distances. That's due to the reactances. And just to make it even more complicated, there's inductive reactance and capacitive reactance, and they both change the way the waveform behaves. HVDC systems therefore require less in the way of cabling, and it's much easier to control the power on a DC system. And the other thing is that it can travel in both directions. If you're sharing power between, say, Norway and Scotland, and at a certain period, Scotland's got plenty of energy generated by wind farms and it needs to shunt that off to Norway, they can do that. They can just change the direction, which is nice for them, but not so nice for the CP guys and the corrosion guys and the people responsible for risks. This is a summary of the kind of interference you get from different energy systems. And you can see that surprisingly, high voltage DC has AC and DC in it. And here we mention induction and conduction. And these are the two main mechanisms for transferring the unwanted power that we're likely to hit. So the reason we've got to talk a little bit about the way the HVDC systems are configured is because it makes a huge difference on the type of interference and the extent of the interference, and that'll become a little bit clearer later on. But induction relates to changing magnetic fields. If you've got a changing field and you've got a conductor in that changing field, it will induce a voltage in it. That's how generators work. It's how radio systems work. Somebody sitting in, I was going to say Luxembourg, but not many of you will remember Radio Luxembourg. But somebody sitting at a radio transmitter in Moscow, say, sending all kinds of propaganda, he's basically sending an electromagnetic wave. And that wave travels around the world, and it comes to your antenna on your radio or your television, and the changing field at the frequency that it's transmitting on induces a voltage in that antenna, and that goes into your radio or television, goes through an amplifier, and lo and behold, you get the message. And it's exactly the same mechanism that we have on the electromagnetic fields generated from varying voltages, AC voltages. And in the UK, as you probably know, that varies 50 times a second. That's the frequency of the electricity that squirts out of your wall socket in the house. Conductive interference is exactly what it sounds like. It's conducted through the medium between the source and the recipient. So in this case, it will be the soil. The electricity travels through the soil onto the pipeline, and it changes the pipeline voltages and performance. And the conductive interference normally only occurs during fault conditions, which is when you might have one of the cables break on your overhead line and it falls to the ground, and that current travels through the ground, hits the pipe and generates upstream and downstream until it finds the compressor station or any above ground area where there's isolation. So having explained to you that DC doesn't vary, you can logically assume that it will have a magnetic field, but it doesn't change. And because it doesn't change, you won't get any voltage induced in it. Unfortunately, this isn't the case with high voltage DC, because as you'll see a little bit later on, we have to do various things to this DC to prepare it and then squeeze it down the line. And part of that results in about a 5% current fluctuation of the DC. And the conductor doesn't care where the interference comes from. The pipeline couldn't care less. But if it gets a magnetic field changing around it, it will induce a voltage in it. And it might only be 5%, but 5% of a big number is still a lot. And with a pipeline, we're in the situation where we have a very narrow band of acceptable voltages on our pipelines, which the standards prescribe for us. And roughly speaking, the difference between a pipeline corroding like fury and a pipeline that's totally passive and not corroding, protected by cathodic protection, is roughly a bit less than a volt. It's more like 0.7 of a volt. Depends a bit on circumstances, but just to understand the principle, we can use these numbers. So you don't want your pipeline voltage varying by more than 0.7 of a volt. And that's a big demand when you've got very high voltages floating around. Now, I don't want to mislead you along the path of thinking, like many people do, that just because the voltage goes into a positive area where you can expect corrosion doesn't necessarily mean corrosion is going to take place. There's I'll call it an inertia. It isn't literally inertia, but there is an inertia that the corrosion process won't start until a certain period has passed. Depending on the circumstances, it can be seconds or it can be minutes. So just because the voltage shoots up and down doesn't necessarily mean you're going to corrode, because the corrosion process doesn't have time to start if it's rapid fluctuations. Now, HVDC systems can be bad news for pipelines because, again, depending upon the configuration, you can have large amounts of current flying around close to the pipeline, which we don't want. And these HVDC systems are cropping up more and more as countries are working together to shovel around the power. If they've got an excess of power, they can shuffle it off to somewhere else. And then in turn, that can go to another country. When the things change, it can change direction. But at the end of the day, we really have to take account of these risks and we have to quantify them. To give you an idea, this is just some recent examples of systems that are going in. There's the Celtic interconnector going over from Brittany to Ireland. There's a green link between Wales and Ireland. There's a Viking link to Denmark. There's some to the Netherlands, and there's a lot more. If you put up a map that showed all of them, it would be too confused to really understand anything about it. But this is the way that people are going. We're collaborating and we're sharing energy, and we're also storing energy more in battery energy storage systems and other types of converters. HVDC's improved a lot. It's been around for a long time. I can remember working on a pipeline in Mozambique about maybe 25 years ago, where there was a high voltage DC power system running down to South Africa from Mozambique. So it's been around for a long time. But the way they work is interesting from our point of view. We have to understand a little bit about this in order to deal with it properly. But you've always got a sender and a receiver, even though they might be different from day to day, hour to hour. Not usually hour to hour, but the day to day. The terminals are configured so that they're bidirectional, so they can either receive or they can transmit it. Modern technology using things called CSCs and VSCs. Yeah, I've put those in because you might come across them and wonder what on earth they mean. It's nothing to concern you very much about the detail. It's just a way of making the systems work, about how it hackles, really. But it does make a difference to the performance and on the interference characteristics. So they've really improved those a lot. They've got them down to a fine art now. It stands to reason that if you're going to transmit HVDC, you've got to get it from somewhere. And what we actually do is we get it from the main grid, the existing AC grid. and we convert it to DC, very much in the same way that you change AC to DC in a battery charger so that you can charge a battery with DC. Although, of course, these are humongous buildings with all kinds of stuff in them. But originally it comes from AC, and it's converted to DC by putting it through a series of special types of diodes. And they sound a bit like LGBT, but it isn't. It's IGBT. And the only similarity, I suppose, is that they're bidirectional. It's an insulated gate transistor that actually does the job. And when you convert AC to DC, you do get some residual AC. You never get perfect smoothing. So the systems have always got a large area to get rid of the harmonics that are generated, because we don't want harmonics. It's just lost energy and causes more interference. And it has to be 50 hertz in order to link in with the grid. You can't just go and simply add something to the grid and think it's going to work. So this is a general schematic, and you can see here that you get your AC in, alternating current in, and then that's stepped up or stepped down depending on what we want to do with it, and then it's rectified, and then it's transmitted across the sea or across the country through a go and a return circuit, which I'll look at in a bit later. And then when it gets to the other end, we have to change it back into AC and then send it on its way. And changing it back into AC is a rather crude process, electrically speaking. You basically chop up the DC very rapidly and then add it into a wave which you build up bit by bit, so you end up with a sine wave. But the process produces harmonics again, so you get harmonics at one end and harmonics at the other end, which can also add to the problems. And some typical outputs for these systems would be 100,000 volts to 200,000 volts for short sections, because you don't get much in the way of losses, 320 to 400,000 for medium capacity, 500 to 600 for the high capacity, and more than 800,000 for very long distances and very high power transfer. And the current outputs will vary between, just put in some rough figures here, between 1,000 and 4,000 amps. So you're dealing with quite big numbers here. And the question is, how does all that cause corrosion? Well, this little drawing, which was put together by Professor Charalambos, illustrates it very well. It's all down to the coatings on the pipes and the cathodic protection on the pipes that are there to protect it. The coating is specially prepared for buried pipelines, and it stops the current leaving the pipeline, because where the current leaves the pipeline, you will lose metal. And from Faraday's law, we know that 1 amp DC for 1 year will consume 9.1 kilos of steel. And in the old days, we had coatings which fell off in sheets. But the modern coatings, the chemical composition of them, the way that the quality control exercised by the pipeline engineers means you get very, very good quality, well adhered coatings which don't fail in the catastrophic ways that they used to. There are obviously still some pipelines around that don't benefit from the new coating technology and the increased QA/QC, but generally you end up with rather small coating defects on pipes, if at all. And that is a whammy for us, because it means that all of our metal loss will take place over this small surface area, which is generally, we give a figure of about a centimetre squared, that has some significance to corrosion people. So we don't really want any of this kind of stuff going on. So in order for you to better understand all of this, I'm going to share with you a slide which will tell you everything you need to know about electricity. And those of you who were present yesterday will understand this easily. Electricity doesn't go anywhere unless there's a slope, like shown on the right-hand thing. Imagine electricity is a bundle of charge traveling from one place to another. That's all electricity is. Just these charges traveling along the pipe or through the soil or wherever it goes through. And that's all it is. But if it's perfectly balanced like this, it won't go anywhere. So if you have what we would call equal weights on this seesaw, let's say they were a ton each, the slope would be zero and the ball or the charge wouldn't go anywhere. If you had 10,000 volts here and 10,000 volts there, the charge wouldn't go anywhere. There would be no current flowing and you wouldn't get an electric shock if you touch the two 10 kV terminals, because they're at the same potential and you're isolated from the ground. So for any current to flow, you need a gradient in the soil. And that gradient is analogous to this little slope here. And that is the root of all the issues to do with stray currents. If you could make everything at the same potential, which is impossible, practically speaking, you wouldn't get any interference or any charge. So when you've got a nice, fat, high voltage DC cable squirting juice into the ground, it very rapidly brings you into this situation. Now, as I mentioned to you before, electric circuits, DC circuits are really simple. It doesn't matter whether you're talking about a button cell in your calculator, or if you're talking about a 33,000 volt HVDC system. If the circuit isn't complete, if that switch isn't closed, you won't get any current flow at all. It's just basic science. And what you can substitute here is the transfer of your high voltage DC from one place to another. You need a complete circuit. All of these need to be complete. You could think of this of the incoming circuit and of this of the outgoing circuit. If you think in electrochemical terms, if you think in logical terms, you can think of this as your transmission to the new station and the return circuit. If there's no return circuit, if that switch isn't open or the cable's broken, you won't get any HVDC current flowing. And this is going to be important to remember when we come to the discussion of the configurations of the high voltage DC systems. So we've got a number of different systems. You can have back-to-back, bipolar, monopolar, and multi-terminal setups. And it just determines how the DC current flows back and forth. And the obvious thing to do is what they did in the old days, in the original days. They said, well, we'll generate this DC, we'll stick a big electrode in the ground, or very often they put it in the sea or close to the coast, and then we'll rely upon the earth to return the current, because the earth doesn't care, it's just a conducting medium. And if the voltage is high enough to drive the current, you can drive it through concrete. So they were very pleased with themselves, because they found that they only needed one fat cable, not two fat cables. So the fat cable costs were reduced by half. But then they discovered that you can have an adverse effect on a pipeline more than 30 kilometers away from one of these electrodes in the ground. So they then went on to bipolar, where they had the two cables, which helps things a lot. But one of the things you have to remember is that the people who generate this HVDC and the AC originally, and then convert it back to AC and then put it into somebody else's grid, they're commercial enterprises, and they get paid by how much they put into the grid and for how long. It's as simple as that. It's like your electricity meter at home. They just count how much goes in and then they get so much money. Well, they would rather run their system at half power and get half the revenue than not run it at all. And that's not good for the pipelines, because a system that's designed to be bipolar, i.e. having two cables with it, produces much less interference. And if we do our risk assessment on the basis that it's a bipolar system, we have to take account of when it's running in monopolar mode, because it can run in monopolar mode. And we also have to take account of which direction the current's flowing, because that can affect the risks of interference. So the return path options, I think, are pretty straightforward to understand. It's either a hard wire or it's the earth. So that's, I think, leads us into looking now at what some of these systems look like. So that's the monopole configuration with electrodes in the soil, and the current travels through the ground, causing all kinds of mayhem. This is the bipolar one, where things go, or should go, via the cables. That just illustrates the filtering and things like that. So you've got your one circuit and then coming back the other way. So when all this is fine, the interference is at its lowest level. You still get a small conductive current due to manufacturing tolerances and so on, which we have to take account of. But you don't have to be Einstein to work out what 2% of 2,000 amps is. It's still quite significant. They will often run it in this emergency mode. You can see they've got the switch here, which is analogous to the little battery and system I showed you earlier. And that means that the current is going back through the soil, which we certainly don't want. So we know that we've got the EMI, which is just a fancy way of saying inductive interference. You get harmonics in the line due to the switching, the way that we switch it and convert it from DC to AC and AC to DC. And then you get abnormal conditions, because they're electrical circuits, they're subject to faults. And when that happens, you can get quite serious effects on your pipeline. And the impact of short-term electromagnetic interference has to be taken into account as well. And we've introduced a term here which is called RMS when we talk about the stress voltages on pipeline coatings. The RMS means root mean square, which is a fancy way of saying that when we calculate how much power a system takes in DC, it's pretty easy. It's just a function of the current and how much resistance there is. When you're talking about AC, you have to change the way you calculate the power if you want to be able to compare with DC. And RMS is the way that we do that. So it just means that 2 kilovolts RMS would produce the same heat as 2 kilovolt DC. So that's why we use that. The difficulty we come to is when we have to evaluate what the risks are and what we need to do to ensure it. And a lot of this information is, I have to say from experience, a source of irritation to the developers of the system or the operators of the system, because they often don't have it. But if I had to distill all of the electrical impact assessment work on pipelines, I would say it comes down to how much power there is and how far you are away from it. And that takes us back to the little seesaw analogy, that if you've got a big voltage gradient, then you're going to travel a lot further. And if you've got a lot of current, that's what drives the big voltage gradient. So you can see that there is a logical sequence in the way that we look at the evaluation. And one day we might be able to spell evaluation. I apologize for that. And this is the procedure that we actually follow for the EMI. There is mitigation that can be applied when the interference gets too high, because we have to recognize that with the best efforts of the designers and operators of the HVDC, there are going to be times where you just can't reduce it anymore. And then we have to do something on the pipeline. We try and avoid that because, as all of you will know who are operators of pipelines, digging down to a live pipeline is not a desirable task. And we try to avoid it wherever possible. But if you get to a point where under fault conditions or under some conditions, the slope, the voltage gradient can be so big that it can exceed the stress voltage on the pipeline coating. The proper name for the stress voltage is the dielectric strength, which just tells you how much difference the material can stand on its two faces. And for pipelines, the coatings that we have, which are fantastic for corrosion protection, are not designed to withstand very high voltages. It's just an accident that they do. And a typical coating threshold would be between 2,000 and 3,000 volts. And it will withstand that reasonably well any number of times. Once you go above those figures, you need to start digging and see, not literally, but you need to start investigating to see what can be done and what you can truly accept. The standards that exist are not good at providing stress voltage figures. In fact, the only one that does is an American standard, which is it's not a standard exactly. It's a guideline written by AMPP, which some of you may know better as NACE, and they reckoned 2 to 3 kV, but they use the same value for FBE and 3-layer PE, which is probably because they hardly use 3-layer PE in the States. A 3-layer PE will withstand a lot more, but you have to check. Now, those of you who are involved with gas systems and you have above ground installations at compressor stations and so on, the pipeline is normally electrically isolated from the AGIs in order to prevent a pipeline being in contact with earthed systems, which would not do the system would not do the corrosion protection system any good. Unfortunately, the dielectric material used in those isolation joints and many of the insulated flange kits won't go much above 2 kV. So you are at risk if you get interference on your pipe, even for a short time, that exceeds that dielectric strength of your isolation joint, because it will just fail. Now, we normally put a diverter or a surge arrestor across the insulation parts of an isolation joint, but all they will do is they will pass that current into the AGI. So if you happen to be working in the AGI at that time, believing that you're protected from these kinds of things, you won't be. The other issue we have is how long an HVDC system is likely to be down due to a fault. Because as I mentioned earlier, the corrosion process doesn't start straight away, but it gets more problematic as the time goes on. And there's no guidance in the standards about this. And Professor Haralambos has done some research in his lab, and he's produced this graph, which is MTTR is mean time to repair. So you can see that the longer it takes to repair, the worse the risk is. Now, to do the assessment, the best way usually to evaluate the risks for a full-blown system is to do mathematical modeling. Now, I'm not a big fan of mathematical modeling for one reason, and that is you can't audit it. It's a big black box. Numbers go in and numbers come out and charts appear and plots and graphs. And the plots and graphs are so good you want to believe them. And most of the time they are correct. But we've done some audits of modeling, and to do that, you basically have to remodel it or remodel parts of it just to see if it ties up with one or two calculations. And because you can't audit it, the only control that you as the layman, as the pipeline operator have is to make sure that the guy who's doing the modeling knows what he's doing. And that's hard for you to do if you don't already have the same level of electrical knowledge as he's got, which is unlikely. So the only way that you can do it is to make sure that the guy is properly qualified. Now, this is still, to a certain extent, cowboy territory in pipelines. There are some very, very, very capable modeling companies around who do the work, and they do it well, and you can rely on them. But there's still a group of engineers or consultants or whatever they like to call themselves who will promote themselves as being expert in this and then just subcontract it out to somebody who can model it. And you do end up with some pretty awful models that are basically not true. And a little bit of common sense will help. If you see that the interference is getting bigger the further away you go, well, that's a bit of a flag because it should attenuate. And there are other criteria that we can look at. You can do the modeling using manual calculations. There's no problem in doing that, except that it just becomes practically impossible to do for a full-blown system. You can certainly get away with doing manual calculations with formulas that have their provenance in standards and science, and you can get a good feel for where it's going. But if you want the whole story, you've really got to model it. And what you have to remember about modeling is it's static most of the time. Some people feel that it will continuously change as the inputs change, but the model is just a snapshot of a certain set of criteria that you've put in at a certain time. So it's not all wonderful, but it is a good way to go. And I think apart from being able to check the competence of the person, which there is one ubiquitous company which produces software called CDEGS, very widely used, and they maintain a formal training program which is tailored for pipeline applications. And what's more, they keep a register of competent persons, and they have to re-register after a certain period. I forget what it is now. It's different for different modules. But the program is very easy to work and very easy to do if you just want to do simple things like substation earthing. It's great for that, and almost anybody can do that with just a few simple lessons. But once you get a pipeline involved, things get more complicated because you can't, for example, just take the 1 kilometre of pipeline that might be parallel to this HVDC cable. You've got to look at the ends of the pipeline as well, how it's terminated, what the resistance is, and all that kind of stuff. So the other thing you could possibly do is ask them to explain the modeling results to you in a way that you understand. And if he can't do it, it probably means he doesn't understand it himself, which is something that's been attributed to Einstein and also to the famous physician or physicist rather, not physician, physicist Richard Feynman. And I think it's a pretty good adage. Not always true. I mean, there are some people who find it difficult to explain things simply, but generally speaking, if they can't explain it to you in a way that you understand, the alarm bell should start to ring. There isn't a great deal of help in the technical standards at the moment for HVDC modelling and mitigation. There are some examples which I've put up there, 50162, 21857, but really there's not enough in there to give you a good steer. And the other thing to bear in mind is that the safety thresholds that the HVDC people adhere to are not necessarily good for us, because, as I mentioned, you really have to remember that the difference between a freely corroding pipeline and one that's fully protected is less than a volt. Well, if you're running a 33,000 volt DC system, you're not going to be worried about the odd volt here and there. So we have to be aware of that. Now, there is a new standard in preparation, and it's being written by the same group that wrote the 21857 standard, which is the one for stray current interference. And I'm the chairman and convener of that working group. And we've been working on the standard for the high voltage DC now for a year or so. And by the end of this year, it should be into a state where it can go out for public comment. We've done our best to cover all bases on it, but in the end, it's a performance standard, and performance standards assume that the person reading them is technically competent. And this high voltage DC, as well as ordinary DC interference and AC interference, actually straddles two specialized occupations. One is corrosion and the other is electrical principles. And not everybody who's an expert in cathodic protection has the electrical background to understand the depth of these standards. So we've tried to cheat a little bit. You can't make it into a textbook, that's for sure. But we've tried to cheat a little bit by putting in what they call informative annexes. We did the same trick in 21857. And we give worked calculations so that people who are competent enough to undertake cathodic protection designs should be able to follow the simplified formulas and come up with some numbers. So that's our contribution to this going forward. So I think that we all recognize we need some guidelines for this, because it is a risk. The people who are running these systems make the argument that, well, we've had it running for 10 years and we haven't had a problem yet, so why are you making this fuss? And I think that's rather analogous to you maybe standing on the pavement with a child, and the child suddenly runs across a busy main road, and by a miracle it gets to the other side. And on that basis, you wouldn't jump to the conclusion that, oh, well, they got across once, they can get across twice. Well, it's the same kind of probability risks here that we have to be aware of. And pipeline operators have to know about these things, because if the pipeline explodes or has a loss of product, or there's some other horrible tragedy, it's not the HVDC people they want to talk to, it's the pipeline operators. And that's what makes us twitchy about these things, and trying to get good guidance and provenance to the guidance so that we can be quite happy that we're doing the right thing. So basically what I'm telling you is that it's complicated. They can operate in different modes, and you need to be careful how you carry out the modelling. Now, if you want any further information, if you follow these links for the research projects that PV Erosion does, you will find a lot of useful information there, a lot of case histories. And you can also contact either myself directly or Professor Haralambos directly via email. So I think that's about all we've got to say. I'd be very happy to take any questions if anybody's put them in the chat, or if you want to vocalize them. We've got a few minutes to take some questions.
And thanks for a great speech. 2 days running that you've given us a great entertainment and knowledge. No questions in the chat at the moment. If anybody wants to ask any questions, do you want to raise a hand? Or David, over to you.
Hi Ken, thanks for that, Ken. It was a brilliant webinar. Sorry I missed yesterday's, but hopefully I'll get it on catch up. Quick question: if I was looking at, let's say, a solar park or another DC system in close proximity to a pipeline, is there anything you'd recommend in terms of reference material to look at let's say, an early feed stage before we'd engage our consult, let's say, to do a detailed design, just at a high level, apart from the standards you've referenced, obviously?
Yes, good afternoon, David. I'm glad you enjoyed the presentation. If I understand the question correctly, you're thinking of a solar park and an HVDC system in the same location, and what you would need to do at the feed stage, the front-end engineering design stage. Is that have I got the question right, David?
Yeah, correct. I suppose we work together. Can from my side, I could come at this from one of two ways, where we're designing a solar park near an existing pipeline, or placing a pipeline near an existing solar park. So it was more, what would be good reference guidelines or reference material to look at them, to see if we're in too close a proximity at an early stage, and then look at alternative physical locations.
Yeah, I think at the front-end engineering stage, David, there are some useful bits of information you can collect. You can look at the soil resistivities. That's always something necessary to work out the rise of potential at the pipeline itself. You could also look at the actual way they design the solar farm, because the solar farm is only going to leak currents either through the insulation resistance between the panel and the framework, or through damaged cables. And you can avoid the risk on damaged cables if you put them in non-metallic sealed ducts. Then there won't be any problem, even if by some miracle you have a pole fault, a phase fault in there. It won't do anything, because it's got nowhere to go, because there's the plastic duct and there's the end sealed. With regard to the separation distances, I think we generally end up in the state where you have to live with what you've got, and you have to consider at an early stage the mitigation that you might require on the pipeline, both in terms of induced AC and in leaking DC. And depending on the magnitude, you may be able to control the effects of the leaking DC with cathodic protection, and you may be able to mitigate the AC using conventional mitigation techniques like zinc ribbons and things like that. And for reference and for provenance, you can refer to 21857, EN ISO 21857.
Brilliant to know. That's very useful. Thanks, Ken.
Okay.
Anybody else? Any other questions? Chris?
Hello. Thank you, Ken. Brilliant stuff, and especially your ability to explain some quite complex concepts so simply for the likes of me. I have a question also about standards that we seem to have a mixed bag of standards from different sources. We've got the AMPP and the NACE standards. We've also got British standards and ISOs and Euro norms as well. As an operator in the United Kingdom, do all of the standards carry equal weight, or should we be perhaps lending more weight to the British standards, Euro norms?
Very good question, Chris. There is a pecking order in standards, and it's the national standards that prevail first. So whatever the national standard says, that's what you have to follow, or you have to justify it. You're right to be wary of ISO standards, and I speak as a man who's worked on ISO standards for 20 plus years, is that they're all written on a consensual basis, which means that you go for the lowest common denominator. So they're not always good guides to use, to rely on. So in terms of electrical interference to pipelines, there is only one standard for DC, and that is 21857. And that is one that both Professor Haralambos and I worked on, and it's relatively recently produced, and it does give calculations which you can copy and calibrate your own spreadsheets with. Some of the calculations are a bit complicated, but we've simplified them as far as possible, and you can at least copy them. The problem with having so many standards, as you rightly say, is you can more or less pick the one that suits you best and say, well, I followed NACE. And that is a road to nowhere, really. But what you can look for is that sometimes there is a NACE standard, for example, which gives you some guidelines on the dielectric strength of the coatings, which doesn't exist yet in any other standard. It will exist in the new standard we're writing for HVDC, because we're going to schlenter it in and put it in an informative annex. But I think you're better off sticking with anything that's got BS in front of it is going to serve you well.
Thank you. That's really helpful.
Anybody else? My own observations were when you were talking about the HVDC system and the Viking Link connection. Our past president, Sir John Butterworth, gave a great talk at one point about the installation of those cables, and a lot of it's unrepeatable because basically we were getting hit by Vikings who were ripping the things up and trying to steal the before it went in. But yeah, there's some great stories behind them as well. But I don't know if we'll get them. Ken, thanks for your time. Much appreciated. Is 6-1 you've done now?
6 or 7, I think, now in this series. It's one of the good things about the Guild is that that we're not all good at the same thing, and that's a kind of a narrow view to have. So it's good to be able to make these presentations to pipeline operators and people who aren't electrical and corrosion specialists, so that they can appreciate why we do the things we do and why we look at things the way we do. And I mean, there are other things that I could have brought in here, like in yesterday, we mentioned the lightning risks, that you might think that a buried pipeline going through a rural field has a very, very low risk of being struck by lightning. But if you build a solar farm near to it or a wind turbine near to it, the risks increase significantly by several orders of magnitude. Now, they might still be within acceptable limits to the pipeline operator, but they have to be quantified. And the same thing's going to happen here if not all HVDC cables are buried. Some of them are above ground, and that increases the lightning risk. And the lightning risk is around about 100,000 amps a pop. And if it happens to be close to the pipeline, it will spread very quickly through the soil and affect the pipeline integrity. So, you know, a pipeline, a pressurized pipeline is a long, thin bomb. That's all it is, with about somewhere between 7 and 20 millimetres between it and catastrophe. And when you can lose metal at the rate of 9.1 kilos per amp per year, and when you've got fault currents of 37,000 amps, not unreasonable, then you don't have to be a genius to work out that this isn't good news.
Yeah, we're nearly at 1 o'clock. Really appreciate it. Thank you. Just for everyone's benefit, 2 more talks coming up next week, one on Cunliffe, one on Reg 31. But please have a look at the, just going to drop the link in the chat for the events coming up on Pipeline Guild. For your time today. Bye-bye.
Bye, everybody. Thanks for coming.
Thank you. Bye.